figure. You can look at the figure 6423, 6422. That's here, right? So this is 6423. The gradient, and so this is principal abrasive EDM. So this is a gradient wheel, and also this is EDM. So here is this is A and B is this is gradient. So this is a two-pulse generator. So here is the gradient. This is the workpiece is grounded, and also here is there's the EDM here. So this is a process mechanism. So you can see this workpiece is being fed this way. Here is the electrical. Here is the electrical. And here, look at here. So here is abrasive grain, the gradient grain. And also here is a discharge. From the EDM. So this here is a combination of EDM and abrasive. This is abrasive, call it abrasive EDM. The removal of the conductive or partially conductive material is by the combination of repetitive spark discharge between the workpiece and the rotating tool. So this is a tool. The spark, both the EDM spark and also the rotating tool, and separated by the by flowing the electrical fluid, and also by a mechanical action of irregularly shaped abrasive particles on the periphery of the wheel. So this is how the gradient wheel works. So simultaneous the synergic mechanical energy and energy of electrical spark discharges increase the machining productivity and improve on surface quality. And so this is the solution for combining these two guys together. And therefore, material is removed by the combining effect of electro erosion from EDM and microcarding from the abrasives, the bond on the gradient wheel. So an increase in performance measures of the AEDG the process becomes evident when machining super hard materials. If the material is very hard, and this is a very, very good option. For example, engineering ceramics, sinter the carbides, and these metal composites. It can be seen from this is another figure we should show you that the MRR increases significantly in this is a combined process when compared with the conventional gradient. So you can see it here. So this is time. This is average the MRR. So here is a conventional gradient. Here is a abrasive EDG with 15 astronauts 15A current, and this is with 28 the current. And this is 28 current is for the EDM. You can see the average MRR can be improved substantially. What is MRR? I forget.
Material removal.
Huh?
Material removal rate.
Okay, material removal rate. Right. Yes, the productivity is an indicator of productivity. Here is a more gradient MRR. So here is a more EDM MRR. Controlling surface finish by changing the intensity of either EDM or gradient surface. If you have, for this case, okay, more EDM, ERI, and so this surface is not good. More gradient MRM, so this is better. Material removal mechanism. So MRR stands for material removal mechanism. Can you write down it? MRR is a material removal rate. MRM is material removal mechanism. How the material is removed, either from because of gradient abrasives or from the EDM. So we can see the surface finish should be optimized based on the requirements of product performance. We just show you if we increase the gradient and the surface finish is better. If we increase the EDM and the surface finish is bad, so it's worse. If the gradient process is allowed to dominate in material removal, the smoother surface finish can be obtained. On the other hand, if the primary objective is faster machining speed, and then EDM will play the major role in the material removal mechanism. So this is IRM stands for the material removal mechanism, and hence comparatively poor surface finish will be obtained. So this is and you should know. For my bottom line is that you know what AEDG is. It's a combination of abrasive gradient and this EDM. And what are the benefits and when we combine these two guys together, you should know that. Okay. Second one is abrasive wear EDM. So here is this is the EDM and then the wear EDM. Wear EDM means that the electrode is wear. This is a wear EDM. So this is this gradient is nearly the same as AEDG, but now this time is wear EDM. In this process, the abrasive grains are embedded within the wear using to perform the wear EDM. So, and therefore, the material removal process is a combination of spark injection. Spark injection actually is EDM from EDM, okay? Then the mechanical operation. The combined mechanical and electrical action helps minimize the recast layer and at the same time enhance IRR. Can somebody tell me what is the recast layer? What is the recast layer? Recast layer means that at the high temperature, the material melts. However, the molten material, and because the cooling effect for some anything, the cooling rate, the cooling the fluids or whatever, and this is the molten material solidifies again. So this is called recast layer. But now you tell me what is the recast layer? Just to paraphrase what I told you. Well, what is the recast layer? Okay, recast layer means that, and for this case, EDM, because the high temperature and some of the material near the sparks, and they melt, okay? They melt because we have the dielectric fluid, and this is a molten material, this molten part, and they will re-solidify. After they re-solidify, another layer forms. This layer is called recast layer. Right now, I might ask you guys. So there are a lot of the word terms in the machining processes. So you should know that recast layer. So the work principle of this one is presented in this figure. I'm going to show you guys. The reduction of elimination of recast layer in AEDM compared to conventional EDM can be seen from another picture. Why the recast layer is bad? The recast layer is bad because you almost have no control of the cooling rate of the molten material, and so you do not know what kind of microstructure or nanostructure you will obtain because of the solidification. So the recast layer is bad. Okay, guys? So you say the research role is that we want to eliminate or minimize the recast layer. Why? Because the recast layer, the mechanical property for the recast layer is difficult to obtain because you do not know what is the cooling rate or what kind of microstructure you will get. So this is you need to test it before you do that. So this is that's the reason this is bad. So 625, 620, this is 625. This is the EDM. This is a wear combination of EDM, wear EDM with abrasive. This is the processes. This is a discharge, and here is abrasive grain. So here is a diamond of it. This is a diamond abrasives here. And so here is a feed and cooling in this direction. And so the B stands for the recast layer formation between WEDM and this combination of operation with the WEDM. So here, this is a recast layer. You can see, do you see this layer? This layer is a recast layer. And here, and this is layer is a recast layer. So this is a recast layer is almost negligible. You can see that. So here is this is very obvious. Look at my mouse there. Look at this green one, green layer, right? But here it is very thin. Can somebody tell me why? Because this guy will remove some majority of it, right? So because it's abrasive. So here, this one happens here first, and then this guy come from here to here. Then we remove majority of the recast layer. So the experiments were conducted on a nickel. This is a nickel 600 alloy to compare the extent of recast layer in the normal WEDM and the advanced WEDM. So see, as a machining of recast the free surface case of interest. So recast layer is bad. This is our second advance in the next one is powder mixed EDM, and it is a micron EDM. Micron EDM means micron as name says, and we produce the micro features. The powder mixed, what is majority of the powder mixed the discharge machine with the previous AEDM is that this is powder mixed EDM. The conductive and the semiconductive powder material are mixed with the dielectric instead of with the two electrodes. And you should know that what is a powder mixed. So this is powders are mixed with the electrical fluid instead of with the two electrodes. This is one difference. Another difference is that the material removal mechanism of both processes, unlike the abrasive assisted, the abrasion action on the powder is very minimal or negligible in powder and EDM. So the powder, definitely, so abrasive assisted EDM, and we use the grading abrasives. But here, we just add some abrasive powders. Definitely, this is very minimal and negligible. So in this new type, electrically conductive powder reduces the insulating strength of the electrical fluid and increase the spark gap between the tool and the workpiece. The EDM process becomes more stable as the flushing becomes easier at a higher spark gap. As a result, the overall machining efficiency, MRR, and SQ, this is improved. So the sparkle is uniformly distributed along the powder particles in the spark gap, and thus reducing the intensity of the single spark, which results in uniform shallow craters instead of single broader craters. So this is the effect, okay? And thus, the surface finish improves. So the characteristic of the powder, such as the size of powder type and the concentration, influence the electrical performance. So this is you can see this reference 72. And so this picture shows the differences in the spark gap, powder density, along with the gap explosive pressure. between between conventional and PM EDM. So 626. So this is a 626. So here, this is a conventional EDM, and this is the electrical oil, the gap size between the electrode and workpiece SG. Right? SG is the gap size, guys, and you write down SG is the gap size, and the power density and gas explosion GP here. So here is a crater. See, it's a deeper crater. Here, this is with powders. And this is gap size to the gap size, powder density, and gas explosion. And we can see we can get a broader or shallower craters if we use the powder. I use the powder one. Next picture shows the surface finish at a different region of mold cavity machined by EDM and PDM, 627. So here, so this picture, this one is fabrication of mold cavity. Okay, so this is the mold cavity without the powder. So this is with powder. So as you can see, a significant reduction of roughness has been observed. This is much shinier and smoother after applying silicon powder. Okay, so the roughness, you know roughness, and this is a smoothness, right? Roughness. The roughness many years ago. Why was your age? And we use the roughness, or we use the smoothness. But then suddenly it changed to roughness. We start talking about the same thing from different perspectives. If the roughness is high, that means it's less smoother, right? Less smooth. If the roughness is low, it is smoother. You understand? That's the difference between the probability of survival, which is reliability, and this probability for failure. Roughness and smoothness, and we are talking about the same thing, same characteristic of the surface, but we use different measurement. If the rougher the surface, that means less smooth the surface is. If the less rough, that means it's smoother. The same thing is much smoother. You can see much smoother than this one without powder. So here is a significant reduction in surface roughness can be observed at every region of the mold cavity of the machining using powder mixed EDM. So this is our third one. Any questions regarding this one? I may ask you guys, tell me all this is new forms of EDM and what kind of benefits they can bring to us. This benefit. Next one is vibration-assisted EDM and also micro EDM. EDM and micro EDM, this is just different skills. So in recent years, the assistance of vibration during the EDM and micro EDM process has been found to be very effective in enhancing machining stability and overall the EDM performance. The higher efficiency gained by the employment of vibration assistance is mainly attributed to the improvement in electric circulation that facilitates the debris removal and the creation of the large pressure change between the electrode and the workpiece, as the enhancement of molten metal injection on the surface of the workpiece. So I want you guys to underscore this part. If you are using any advanced the electronic devices, you can underscore it. Okay? I will ask you guys, why vibration assistance can help the EDM? So the high efficiency gain by the employing of vibration assistance is mainly attributed to improvement in circulation that facilitates the debris removal and creation of a large pressure change between these, as an enhancement of molten metal injection from the surface of the workpiece. So this is how the vibration assistance help EDM in terms of high efficiency. Another thing is that vibration assistance, and we can change the microstructure of your material after finishing. And I want you guys to write down, okay? So research has conducted on the feasibility of both electronic and low frequency vibration during EDM. You can see, guys. I want you guys to also write it down. I want you to write it down. The vibration assistance can also change the cooling rate. Change the cooling rate of the dielectric fluid on the machine surface. As a result, microstructure or nanostructure can be changed. That's done. What I'm going to ask in the final is that, using your own words to tell me how the vibration assistance and help people in EM in terms of machining efficiency is one question. Second one is in the alteration of microstructure and nanostructure. Okay.
What was the part you said how it helps in terms of efficiency?
Here, efficiency means because it is vibration. This is an improvement in the electrical circulation, so you can just flush away more quickly the debris under the debris removal, facilitate debris removal. So this is in terms of efficiency. Another one is change. Change the microstructure and the nanostructure. How? Vibration will alter the cooling rate. Right down. This is what I want you to know. Cooling rate. So we can use both ultrasonic and low frequency vibration during EDM. So the vibration has been applied in both the tool electrode, and you can vibrate the tool electrode, or you vibrate the workpiece. It is found that tool electrode vibration can be applied more efficiently in conventional EDM as applying vibration to several micron tool electrodes will affect the micron EDM performance negatively. So on the other hand, workpiece vibration assistance has been found to be suitable for both EDM and micro EDM. So although the vibration assistance is found to be more effective on micro EDM building and fabrication of micro features, it has been practiced in conventional die stacking and wire EDM also. So this picture shows the developed vibrating device and vibration mechanism for generating tool vibration, workpiece vibration, 28 and 29. I'm going to show you that. And this is 28, and this is PZT is a piezoelectrical transducer. And so this guy can vibrate mechanism of applying vibration to the tool electrode. This is electrode. So here is to the workpiece. So you can see this is the platform, and this is the PZT actuator. So this is basic branches. So here is the platform. So this is a workpiece, and electrode will be here. So this guy will be vibrating this way. So here it is vibrating this way. Okay. And as you can see, so this picture shows vibration assistance, the impact of vibration assistance. So here is a microstructure with non-circular cross-section and by workpiece vibration assisted macro EDM. This is very, very beautiful. See? So here, the high aspect ratio This is 4. What is the highest span ratio, guys? I forget. Just something remind me. Well,
Is it a high ratio between depth to diameter?
yeah, or vice versa. Okay? As long as so, this is the dimensions. They are not comparable at all. So one dimension is much longer than another one. This is called high aspect ratio. For instance, this is very deep hole, but with a very small diameter, or very big diameter, but very small this depth. You understand? So this is a basic concept you should know that. So this one. This is using vibration assisted powder mixed medium. They both look like vibration assistance. Is there the powder mix also? And so here is a profile surface. You can see. This is vibration assisted. Any questions with respect to this is vibration assisted one? No vibration assistant? No question? And then we move on to the next one, the fifth one. EDM, micro-EDM slash, and an ECM. And ECM is electrical chemical machining process. So this is very interesting. One the EDM, one the ECM. And to improve the surface finish generated by EDM and micro-EDM. ECM uses a chemical, electrochemical machining process. The surface machined by EDM is relatively rough and due to micro craters and cracks produced by the micro discharges. And then you just use the deionized water discharges. So the deionized water is used in the combined process as it can be serve as the dielectric and in the EDM process as well as can work as electrolyte the medium for ECM at a certain machining condition. So the surface after applying ECM becomes much smoother compared to that of EDM, as well as peak to valley difference of craters reduced significantly. So this is ECM. So you can have this is shows ECM. This workpiece, this electrode, and also this is the electrode within here, and we have some this is deionized water. So in addition to sequential EDM and ECM process, we can provide simultaneously concurrent EDM and ECM process, and have also been reported and in which the discharging or dissolution. So discharging from EDM, dissolution is from the ECM because of chemical reaction of electrical discharge and anodic dissolution. The concurrent EDM and ECM processes have advantage of both higher IRR and improved surface finish due to combined action. This picture I'm show you shows the discharging and anodic dissolution steps and the corresponding change in gap during the micro EDM and ECM processes. The improvements of surface finish both for compound and hybrid processes are present in next figure I'm going to show you. In addition to application of combined process in plasticing, the ECM assisted wear EDM is also investigated and for the machining of low resistance silicon wafers, high efficiency of slicing techniques with low wear consumption is achieved by the use of specific deterrent capability of electrodes. So here is one. So this is a vertical feeding. So A is vertical feeding. And so here is a discharge, the feeding, and here is a discharge, EDM discharge. And C is a dissolution. And D is a horizontal, this is a horizontal feeding, and D is a horizontal feeding. And C, this is C. Dissolution, and this is a horizontal feeding in this direction. And so here is a picture. Surface generated by EDM. You can see this is a kind of rod. By the ECM followed by EDM, the sequential surface. So these are surfaces generated by EDM milling process. And we talked about EDM milling already, right? Now here is by this is EDM and ECM concurrent simultaneous. This is very interesting. You can see very clear. You should know what is the ECM. ECM is electrical, the chemical processing. It's also called anodic dissolution. And then we talk about next one. Next one is magnetic field assisted medium. So this is, as the name suggests, and we put this magnetic field onto something. So it is a process where magnets are attached to EDM near the machining zone. The strong magnetic force are developed by the magnet, and show you in this figure 3.2. So here, so this is an electrode. So here is a workpiece, and we have a magnet here. And this is N polar N and polar S. So we have two polars, N and S. So magnetic flux rotating. This guy is rotating, and with 1,200 RPM. This guy is rotating, right? Rotational disk. So this is the debris. You can see the debris is the driven force from the magnetic field. This is the driven force from the magnetic field. So accelerates the removal of debris from the machining zone and thus assists in efficient removal of debris. So this is the in terms of this is higher efficiency. The gap condition of EDM and would significantly affect the stability of machining process. The gap condition. So the machining performance would be improved by expelling debris from the machining gap faster and easily, implementing magnetic force perpendicular to the electrode rotational force and produces a resultant force that is efficient in transport debris out of the hole through machining. So a debris particle in a magnetic field assisted micro EDM is subjected to two kinds of force, namely the magnetic force and the centrifugal force. Magnetic and centrifugal. So the resultant force on the debris particle is given by the vector addition of the magnetic force and the centrifugal force. Vector addition, and we use the vector addition of parallelogram. You guys know that one? Vector 1, vector B. What is the resultant vector? We use the principle of parallelogram. Which helps to flush out the debris particles from the machining zone, thus improving the machining stability. MRR, reducing two wear and overall improving EDM performance. So this has been reported for magnetic material. The MRR increased nearly 3 times that of the whole part without magnetic material. So this is a very, very effective way to drill holes. So this is 3.2 show that 3.3 ANB shows the improvement in the MRR and reduction in the recast layer thickness. So the increment in aspect ratio of microhole in magnetic field can be understood from figure 33. So here is the 33. You see? And then we'll go one by one. So here is the material removal rate, MRR. So here is the electrode, workpiece, and conventional EDM. So this is magnetic force assisted. So these are conventional EDM. You can see it goes very, very fast. Right? Let us go substantially to how many times. about at least 8 times. Here, conventional EDM, magnetic force EDM, you can see the layer crack, you can see the crack, you can see the layer, and so these are because the layer is so big, you can see in the mountain. It is because layer. So this is because layer with the magnetic force. You can see the hole. So this is the depth of the hole. The diameter is comparable for each other, but here the depth increases substantially. Okay? So this is the magnetic force assisted EDM. And then we talk about another one, laser. The laser is a very widely used machine technology now. So people use the laser to assist EDM and EDM and micro EDM. So one of the major problems with EDM and micro EDM is lower machining speed. And laser machining has comparatively higher machining speed, although it suffers from the formation of heat affected zone and the recast layer. So you can see recast layer is always bad. The accuracy is also an issue in laser machining. I have laser. Sometimes I can bring you guys to my laser lab. And therefore, we combine laser and EDM together and can reduce the negative effects of each single process. So this is combined process, which is called laser assisted EDM, has been found to be useful for micro assembly and for drilling high quality holes. So a novel process has been deployed to solve the issue by combining the micro EDM and the NDIAT laser welding workstation in one single setup. Laser welding means that we use the laser to melt the multiple material workpiece and then we put them together. The micro EDM process fabricates the parts, and this laser performs microdroid to produce the assembly, and so the whole process from micro fabrication and to micro assembly can be completed on the same system. So this is called compound. The NDYG laser possesses the advantages, features of heating concentration and rapid cooling, and is well suited for micro welding. And this can overcome the problem of small dimensional assembly. So this picture shows an example of pin plate assembly by the combined micro EDM and laser welding process. And the pin, I'm going to show you. The pins are fabricated by micro EDM and welded to the plate by laser spot welding. So here, the pin and the plate micro assembly by EDM and laser. So here is a plate. So this is fused and separated end. So this is the whole. No, sorry, this is a pin, and these two guys are welded together. This is a B microstructure machine by combining micro EDM and laser ablation. So this here you can see. This is machined by micro EDM, so this one by laser ablation. And laser ablation uses the laser to machine something. Okay, so this is so in addition, sequential laser and micro EDM process have been invented in order to machine high aspect ratio inclined hole with less burr and recast layer. A laser beam first drills a parallel hole, then an end mill is used to machine the diffuser portion of the hole and provides a flat surface for the drill intention step, a micromechanical building. I'm going to finish the course. Finish this one very quickly. Tomorrow we'll combine the micro EDM drilling and laser ablation process was reported. A hybrid machine tool was developed to combine ultra short pulse laser ablation and micro EDM drilling in one setup. And no reclamping is necessary in this one. So the limitations and the challenges of the single process have been reduced in the proposed pilot process. So this is I'm going to stop now. And then we talk about next time we talk about research progress for national and many media. Thank you very much, guys. So what I emphasized during today's class, you need to slow down, right? These